Hello everyone to this video part 4. So let's continue on our questions of this CSCA paper or CSCA exam. We are at question 16. We have here regarding the momentum theorem. Which of the following statements is correct? So for A, we have the impulse of the net force acting on an object is equal to its momentum. And for B, the impulse of the net force acting on an object until that it's the same as the A proposition, equal to the change. Look at this. The only difference between A and B is we've mentioned here the change in its momentum. For C, the impulse direction is the same as the momentum direction, and for the impulse is a vector, momentum is a scalar. So if we want to answer this question, we need to just like to know what is the momentum theorem. It says that the momentum or the impulse, which is the force times or the net force times a certain time, would be equal to the change in momentum. This is another formula of the Newton's second law actually. So here, if we take the A, there wouldn't be any word about the change, but for B we have it's equal to the change. This delta means the change in the momentum. If we take the F, delta T is delta P, that means the F would be delta P over delta T. That means it's equal to the delta mv divided by delta T. If the m is a certain constant, it's not changing the mass of the object, that must be get out of the change. What's remaining inside the change is the velocity divided by delta T, and this is the acceleration. So we conclude the Newton's second law, F equal ma. This is F net for sure. So for the C, we have the impulse direction is the same as the momentum direction, not necessarily, but the impulse has the direction of the change again. We keep seeing the change of the momentum, not only the momentum. Sorry. For B or for D, impulse is a vector, momentum is a scalar. Not actually, impulse is a vector, momentum is a vector as well. Okay, so both of them have a direction and magnitude. Okay, so the answer is B. Let's move to the 17. In a perfectly inelastic collision between two objects, the systems before and after the collision. For A, we have conservation of momentum, conservation of kinetic energy. Momentum is not conserved, but the kinetic energy the kinetic energy is not conserved as well. For the C, we have momentum is conserved, kinetic energy is not. Momentum is not conserved, kinetic energy is conserved. We have some specific cases for elastic collision and inelastic collision. For these two, we have for this one we have conservation of momentum and we have conservation of kinetic energy. But for this one, we have conservation, for the inelastic collision, we have conservation of momentum, but the kinetic energy is not conserved. Because in the inelastic collision, we have two objects, for instance, will be collide and will stick together. That means they would have a common velocity. Common velocity, there would be a change in velocity, would be change in the mass of the whole system. The mass of this one was, for instance, m and m prime, but after the collision, if they stick together, it's gonna be m plus m prime. So the mass and the velocity will change. That means the kinetic energy would be lost, and it's not gonna be destroyed, but it's just converted into another form of energy, just like heat, deformation, or even the energy responsible for the sound that would be made after the collision. So after all what have we seen here, we can just like choose the momentum is conserved, kinetic energy is not conserved. The C would be the correct answer here. So because it is inelastic, if it was elastic, the kinetic energy would be conserved as well. For 18, we have here, for 80, a particle moves in a uniform circular motion with the radius r and period t. What is the magnitude of its centripetal acceleration? In the course, in the class, you all see that in a curvilinear motion in general, A is decomposed into two components, a tangential one and a centripetal one. Tangential one is just like the derivative of the velocity by time, and the centripetal one is just like the square of the v by the radius. Okay, so we are talking here about the centripetal one. AC would be v square divided by r, but what is the v in terms of radius and period t? The circumference is 2 pi r divided by the time. This is the definition of a velocity as a magnitude. It's distance divided by time. So the distance traveled by the object is the circumference of the circle. The time taken to just like complete one revolution is t, the period. So if we came back here, the AC would be 2 pi r divided by t squared times 1 over t. Let's make it as we have here 4 pi square, sorry, it's 1 over r here, r squared divided by t squared r. We can get rid of 1r here and this r. What's remaining is AC would be like 4 pi squared r divided by t squared. Let's look for this expression among these four statements. The one is correct is actually the A. For the next one, 19, which of the following statements about work and energy is false? Pay attention here, we're looking for the false one. Is A false, or B, or C, or D? Let's look each one by one. So we have here A, work is a measure of energy conversion. Friction always does negative work. The work done by gravity is independent of the path. The net force does positive work on the object, and the object's kinetic energy increases. So here for A, work is a measure of energy conversion. Actually, we do have already we have seen that the A is actually correct, because the work is physically defined as a process of transferring energy from like a form to another form. So the A is correct. For B, we have friction always does negative work. This is not correct actually, because we have two types of friction. We have what we call kinetic friction and we have what we call static friction. For kinetic friction, it's the friction that may be between two objects once an object is sliding over another. If we take a block that is sliding on a certain surface, there would be friction between the two. That's what we call kinetic friction. So the relative motion is toward the right, for instance. The friction are toward the left, so the angle between the two would be 180 degrees. The work would be negative in this case. If the static friction are made, let's presume that the static friction are between the ground and the foot of the certain person that walks. So these friction are responsible to make this person to move forward, and the direction of this friction for sure are into the same direction. In this case, the work would be positive. That means friction always does negative work is a false proposition here. In the case of static friction, that friction makes or generates what we call a positive work. For C, the work done by gravity is independent of the path. This is correct because gravity G, or the weight of a certain object, is a conservative force. That means the work done by those by this force is just like depends on the initial and the final state. It's not depending on the path traveled. So this is not the answer. The net force does positive work on the object, and the object's kinetic energy increases. That is correct. This is what we call the work energy theorem. The net work is the change in the kinetic energy actually. So delta K. We have here, if this is a positive, that means the delta K is a positive, which means 1/2 over 1/2 mv final square would be positive or greater than 1/2 mv initial. That makes that the final velocity is greater than the initial velocity. So the kinetic energy would be increasing if the net work is positive. For the final question for this video, we have here: on a smooth horizontal surface, an object of mass m starts from rest and moves under the constant horizontal force F. We are pulling this object with the constant force F. If it's displaced by S, that means from here to here, we have all this path is just like S. Delta T is this T. The power of the force F is, which one is correct from this list? We have a Fs divided by T, Fv, Fs divided by 2T, none of the above, because there was a motion, that must be a power, that must be a work, means there is a power. So let's just like make this clear in details. What do we have as a power? We have here two expression that's expressing the power. It's either they want us to know what is the average power or instantaneous power, but because it's not specified here in our case, so we're gonna need to work on the average one. What is the average power? It's just like the work done by the time t, and as we see, we have seen the work is just like the force times the displacements. So we can conclude that the average power is just like Fs divided by T. So that leads us to choose the A as an answer for this for this question. For the V or for the B, power is F times V. That would be correct if they were asking us for the instantaneous power, because the force will be changing as the motion is changed from rest to a certain velocity, which is different from 0. For C, it's clear it's not correct. For D, it's not correct. I hope this makes sense for your understanding, and we'll start electromagnetism in next video. As I say all the time, don't forget to subscribe, don't forget to hit the bell so you get notified once the video is posted, and you can just like post your questions or clarification in the comments below. See you in the next video.